Have you ever looked up at the moon, that bright, silent guardian of our night sky? It feels permanent, doesn't it? A constant presence in the cosmic ballet. But here's a little secret. Our moon is slowly but surely moving away from us. A runaway companion on an epic, multi-billion-year journey. This is a fundamental truth of our Earth-Moon system. A slow-motion breakup written in the laws of physics. Over immense timescales, we see a gradual loosening of a gravitational bond that shaped life on Earth. A cosmic drama unfolding above our heads, too slow to feel without science. This is not a sudden departure. Think of it like partners slowly drifting apart, more space between them over time. The moon isn't angry nor pulled by a mysterious force. Its retreat comes from its intimate gravitational relationship with Earth. The same forces that give us ocean tides drive this separation. An intricate dance of energy and momentum between our spinning planet and its satellite. Every wave that crashes is a tiny whisper of this story. The moon has been a source of wonder, myth, and scientific curiosity. It has guided sailors, inspired poets, and served as the ultimate destination for human adventure. So, how fast is our lunar companion making its exit? Is it something we should pack our bags for? Not at all. The rate of the moon's retreat is incredibly slow, almost imperceptibly so from a human perspective. Each year, the moon moves approximately 3.8 centimeters, or about 1.5 inches, farther away from Earth. To put that into perspective, that's roughly the same speed at which your fingernails grow. Imagine waiting an entire year just to see your fingernails get a tiny bit longer. That's the pace we're talking about. It's a cosmic snail's pace. We know this precise measurement thanks to some brilliant science left behind by the Apollo astronauts. During their missions to the moon, they placed special panels called retroreflectors on the lunar surface. These are essentially sophisticated mirrors. Here on Earth, scientists at observatories can shoot powerful laser beams at these reflectors. The laser light travels to the moon, bounces off the mirrors, and returns to Earth. By measuring the exact time it takes for the light to make this round trip, a journey of about 2.5 seconds, scientists can calculate the distance to the moon with astonishing accuracy, down to a matter of millimeters. This ongoing experiment, running for decades, provides the concrete evidence for the moon's slow but steady escape. Why is this happening? The answer lies in a fascinating gravitational dance between the Earth and the moon, a celestial tug-of-war that involves our planet's oceans. It all starts with gravity. The moon's gravity pulls on everything on Earth, but its pull is slightly stronger on the side of the Earth facing it and slightly weaker on the side opposite it. This differential pull is what creates the tides. It stretches our planet ever so slightly, creating two bulges of water, one on the side closest to the moon, another on the far side. These are the high tides we see at the beach, a direct and visible consequence of the moon's gravitational embrace. Now here's the crucial part. The Earth spins on its axis much faster, once every 24 hours, then the moon orbits around it, which takes about 27.3 days. Because of this rapid rotation, the Earth effectively drags those tidal bulges slightly ahead of the moon in its orbit. Let's travel back in time, not just a few centuries, but millions of years. Let's go back to the Cretaceous period, about 90 million years ago, when mighty dinosaurs like the Tyrannosaurus rex roamed the Earth. If you were to stand on the planet back then, you would find a world that was familiar in some ways, but profoundly different in others. The continents were in different positions, the climate was warmer, and most importantly for our story, the days were shorter. Because the moon was closer to Earth back then, its braking effect was stronger, and the planet spun faster on its axis. The Earth was a more energetic, rapidly spinning version of itself. Scientific evidence for these shorter days comes from a fascinating source: ancient fossils. Some types of ancient bivalves, like clams, laid down daily growth rings in their shells, much like trees have annual rings. By studying the patterns in these fossilized shells, paleontologists can count the number of days in a year from that geological period. Now, let's fast forward not just a few years, but far into the distant future. If the moon continues its slow escape and our days continue to lengthen, what will Earth be like hundreds of millions of years from now? The trend we see from the past will continue. Just as the days have lengthened since the time of the dinosaurs, they will continue to lengthen into the future. The process is relentless. Our 24-hour day is not a permanent feature of our world. It is a temporary state in the long, evolving life of our planet. Imagine a future Earth, perhaps 200 million years from now. A day might last 25 or even 26 hours. This change, while gradual, would have profound consequences for the planet's climate and ecosystems. Longer days mean longer periods of continuous sunlight and longer nights. This would lead to greater temperature extremes between day and night. If we push our timeline even further into the future, we approach an ultimate endpoint for this process, a state known as tidal locking. This is the destiny of the Earth-Moon system. A tidal lock occurs when the rotational period of a celestial body matches the orbital period of its partner. We already see this with our own moon. It is tidally locked to Earth. That's why we only ever see one face of the moon. It completes one rotation on its axis in the exact same amount of time it takes to complete one orbit around Earth. From our perspective, it seems not to be spinning at all. In the unimaginably distant future, billions of years from now, the Earth is destined to become tidally locked with the moon. The moon's retreat and the slowing of Earth's rotation will continue until one Earth day is the same length as one lunar month. At that point, a day on Earth will last for about 47 of our current days. The Earth and Moon will face each other in a fixed embrace, like dance partners who have finally stopped spinning and are now just holding each other in a locked gaze. One side of the Earth will perpetually face the Moon, while the other side will never see it. The Moon would hang motionless in the sky for half the planet. When this happens, the great engine of the tides will grind to a halt. Since the Earth's rotation would finally match the Moon's orbit, the tidal bulges would no longer be dragged ahead of the Moon. While the Earth and Moon are slowly evolving towards a tidal lock, a much larger and more dramatic cosmic event is looming on the horizon. Our Sun, the star that gives us life, is not eternal. Like all stars, it has a finite lifespan. It is currently a middle-aged star, steadily fusing hydrogen into helium in its core. But in about 5 billion years, it will run out of hydrogen fuel. When this happens, the Sun will begin a new and final phase of its life, swelling dramatically to become a red giant. This transformation will spell the end for the inner solar system as we know it. As the Sun expands, its outer layers will billow outwards, engulfing the orbits of the inner planets. First, Mercury will be consumed, then Venus will be consumed. The Sun's expanding photosphere will likely grow large enough to swallow the Earth itself. Our planet, along with its now distant moon, will be vaporized by the intense heat and dragged into the fiery plasma of the dying star. The billions of years of geologic history, the evolution of life, and the intricate dance of the Earth and Moon will all be erased in this final stellar cataclysm. The tidal lock we spoke of may never even be fully achieved before this ultimate deadline arrives. Even if Earth were to somehow survive being directly engulfed, the conditions would be utterly inhospitable. The intense heat from the expanding Sun would boil away our oceans. It would strip away our atmosphere. It would bake the surface of the planet to a cinder. To understand all of these grand cosmic processes, from the tides to the orbits of planets, we must appreciate the fundamental force behind it all: gravity. Gravity is the universal glue. It is the force of attraction that exists between any two objects that have mass. It's not something you can see or touch, but you feel its effects every moment of your life. It is the force that holds you to the surface of the Earth, preventing you from floating off into space. It's what makes an apple fall from a tree and what keeps the very air you breathe from escaping into the cosmos. The strength of gravity depends on two things: mass and distance. The more massive an object is, the stronger its gravitational pull. That's why you are stuck to the Earth and not to a nearby bowling ball. The Earth is immensely more massive. The closer you are to an object, the stronger its pull. This is why the Moon, despite being much less massive than the Sun, has a greater effect on our tides. It is vastly closer to us. After hearing about runaway moons, slowing days, and dying suns, you might feel a little bit of cosmic anxiety. It's a natural reaction. The universe is a vast and sometimes violent place, operating on scales of time and energy that are difficult to comprehend. But here is the most important takeaway. You have absolutely nothing to worry about. All of these processes, the Moon's retreat, the lengthening of our day, and the eventual expansion of our Sun, unfold on immense geological and astronomical timescales. They are so slow that they are completely irrelevant to our daily lives, or even to the entire history of human civilization. The 1.5 inches the Moon moves away each year is a distance you wouldn't notice if it happened right in front of you. The slowing of Earth's rotation adds only about 1.8 milliseconds to the length of a day every century. That's less than the blink of an eye, spread out over 100 years. You will never experience a day that feels noticeably longer than the one before it. So the next time you look up at the moon, don't see it as a runaway companion abandoning us. See it as a partner in a slow